Hi folks, in this video we're going to be looking at why organic compounds are coloured, so please keep listening. Okay, let's have a little recap. So chemical compounds are coloured because they absorb visible light. Your colour occurs when electrons absorb wavelengths of light and they are promoted to higher energy levels. However, most organic molecules appear colourless. If we have a look at our molecular orbital here, so your photons that are released promote electrons from your bonding orbital, so the one with lower energy, up into your anti-bonding molecule, which has got higher in energy. So that's where your sigma and your sigma star. You can also have a pi and a pi star as well. Again, pi star are usually empty because they have much higher energy, but because of this, there are several different transitions that your electrons can do. Only some organic molecules are coloured. The ones that only have sigma bonds are colourless. So why is that? So we've got a little diagram on the left hand side here. We've got bonding, bonding, non-bonding, anti-bonding, anti-bonding orbitals. So if we have a look at your sigma bonding orbital, that is the highest occupied molecular orbital, which has got the phrase HOMO, and the lowest unoccupied molecular orbital is your sigma star anti-bonding orbital, again with the phrase LUMO. That's quite a huge jump if you have a look at this little first electron transition here. And because of that, it's such a large jump in energy, what that means is that energy transposes to the UV section of the EM spectrum. Again, you should know that UV light, we can't see it. So no visible light is absorbed, therefore your compound is colourless. However, if you've got pi bonds, you can have a look from the transitions here. Actually, I'll change colour so you can see it a bit more clearly. They are much smaller, therefore the energy that is produced will correspond to the visible part of the EM spectrum, which means that we will be able to see it. Here we have two molecules, they both are coloured, and you've basically to spot the difference. So feel free to pause the video and have a look and see what you can see. But I'm going to highlight the most important things here in the molecule, and I want you to see if you can tell me what this is. Do you recognise it? Could you tell me what it is? Molecules have something what is called alternating double bonds. That is called conjugation. Now this conjugation is part of the it's delocalised along the length of the chain. So if we flick back, what that means is their little electrons kind of whizzing all the way around here, which means that we can have slightly different transitions, which means that we could make colour in our molecule. What that does is it lowers that gap between the HOMO and the LUMO. So again, let's just draw one in here, for example. That could technically be your sigma star, and that could technically be your pi star. And with that lower in energy, that means that more transitions are possible, which means that we've got more energy that relates to the UV, not the UV, the visible part of our EM spectrum. So the more delocalised electrons, in other words the number of double bonds, the smaller that energy gap will be. What that means is the colour will then absorb light of the lower energy, so it's closer to the red end of the visible part of the spectrum. So molecules with lots of conjugation were more likely to have a red colour, and molecules with less conjugation were more likely to have a yellow colour. Okay, here's a summary. So the energy difference between the HOMO and the LUMO determines the wavelength of the photon emitted, and HOMO stands for the occupied molecular orbital with the highest energy, or the highest occupied molecular orbital. And LUMO is the unoccupied molecular orbital with the lowest energy, or the lowest unoccupied molecular orbital. A conjugated system in an organic molecule can reduce the energy difference between the HOMO and LUMO, and what that means is that the energy required to absorb electrons to promote them is going to be less. And finally, the part of the molecule responsible for causing that colour is what we call the chromophore. Visible light is absorbed by the electrons in that chromophore, which can then be promoted to a higher molecular orbital and therefore cause that transition to make different colours. So for example, with vitamin C, it's all the parts that are in red. If you flick back to the molecule, it's that conjugated system of alternating double bonds. That is your chromophore, because that causes your electrons to be promoted. And that's the video finished on why organic molecules are coloured. So remember, it is organic molecules that contain pi bonds, so double bonds or triple bonds, that are coloured. Your conjugated system, which is a series of alternating double bonds, is responsible for that colour. The more conjugation you'll have, the more likely the colours to be red. The less conjugation you'll have, they're more likely to be yellow. and that part of that conjugated system is called the chromophore, which is why organic molecules are coloured.